Welcome! In this session, we'll explore a fascinating problem from LeetCode, problem number 533, titled Lonely Pixel 2. We'll delve into the problem requirements, different approaches to solving it, and analyze their trade-offs. Let's get started. In this problem, we are given a binary grid called picture, which has dimensions mxn. Each cell in this grid contains either a B, representing a black pixel, or a W, representing a white pixel. Our goal is to find all the black pixels that meet two specific conditions. Firstly, the black pixel must be located in a row and column where there are exactly n black pixels. Secondly, the entire row and column containing this black pixel must have the exact same set of black pixels, meaning the patterns of black pixels in the row and column must match. Once we identify all such pixels, we return the total count of these black lonely pixels. The input consists of the binary grid picture and the integer n, which specifies the required number of black pixels. The output is an integer representing the count of the black lonely pixels that meet these conditions. Let's look at an example to better understand the problem. Here, the input grid picture is a 4x5 matrix, and n is given as 2. The grid contains both B and W values, with black pixels distributed across the rows and columns. Our task is to identify rows and columns that contain exactly 2 black pixels each and also have matching patterns of black pixels. The output for this example is 2, which represents the number of lonely black pixels that satisfy the conditions. We'll now explore why the output is 2 by breaking down the matching rows and columns. In this example, we find that row 0, which contains exactly 2 black pixels, matches the pattern of black pixels in column 1. Similarly, row 2, which also contains exactly 2 black pixels, matches the pattern in column 3. These matching rows and columns confirm the conditions specified in the problem. As a result, there are 2 black lonely pixels in this grid that meet the criteria, giving us the output of 2. This shows how the problem involves not only counting black pixels but also ensuring that rows and columns align in their patterns of black pixels. Now, consider a second example where the grid is a 3x3 matrix, and n is 1. Here, no row and column have the same pattern of black pixels while also having exactly 1 black pixel. For this reason, the output for this case is 0, as no lonely black pixels meet the given conditions. Finally, we should keep in mind the constraints of the problem. The grid can be as large as 10,000 cells, so our solution needs to be efficient when checking rows and columns. Additionally, if no rows or columns satisfy the condition of having exactly n black pixels, the output will always be 0. This ensures that our approach must handle both edge cases and large inputs effectively. To approach the problem, one straightforward method is the brute force approach. Here, the goal is to iterate through the entire grid and check each black pixel to determine if it meets the conditions of being lonely. For a black pixel to be considered lonely, 2 criteria must be satisfied. First, the row it belongs to should contain exactly n black pixels, and second, all those n black pixels must appear in the same columns, with those columns also containing exactly n black pixels. The steps for this approach involve counting the black pixels in each row and column, and then validating each black pixel against these counts. While this method is simple to understand, it has a significant drawback. The time complexity in the worst case can reach m*n*m plus n, as every pixel requires rechecking the rows and columns it belongs to. Additionally, the space complexity is m plus n, to store the row and column counts. This makes the brute force approach inefficient for large grids, as it redundantly checks the same information multiple times. Now, to address the inefficiencies of the brute force approach, we can use an optimized strategy by pre-processing the grid to reduce redundant checks. The key insight here is that we only need to focus on rows and columns that meet the condition of having exactly n black pixels. By grouping rows with identical patterns of black pixels, we can minimize the number of comparisons required. Using a hash map, we map these row patterns to their counts, while also tracking the columns associated with each pattern. Then, for each valid row pattern, we verify if the corresponding columns satisfy the condition of having exactly n black pixels. This streamlined process avoids iterating through every pixel individually. The optimized approach has a time complexity of m*n, as it processes the grid and validates rows and columns efficiently, with a space complexity of m*n, to store the row patterns and associated data. This method significantly reduces redundancy, making it much faster for larger grids. Given the trade-offs, the optimized approach is the preferred strategy for solving this problem due to its efficiency and scalability. By grouping rows with identical patterns of black pixels, the process becomes highly streamlined, as rows that do not meet the criteria of having exactly in black pixels can be quickly filtered out. This reduces the number of checks needed and allows for cleaner, modular validation of rows and columns. Additionally, the separation of concerns, first validating rows based on patterns and then verifying columns, keeps the logic clear and avoids unnecessary complexity. In contrast, while the brute force approach is easier to implement, its inefficiency renders it impractical for larger grids, particularly when the dimensions approach 10 to the power of 4. The optimized strategy strikes a balance between clarity, performance, and scalability, making it the ideal solution for this problem. The problem requires us to identify lonely black pixels in a grid. A black pixel is considered lonely based on three conditions: the row it resides in must contain exactly in black pixels, the column it resides in must also contain exactly in black pixels, and the row configuration of such black pixels must be identical to the configurations of other rows contributing to the column counts. To solve this, we start by parsing the input and setting up our data structures. The grid is represented as a 2D list, and we prepare two auxiliary arrays, row_count to track the number of black pixels in each row and col_count to track the number in each column. These arrays allow us to quickly validate the row and column conditions while iterating through the grid. This initial setup is crucial for efficient computation in the steps that follow. Next, we count the black pixels in each row and column. By iterating through the grid, every time we encounter a black pixel at position I, j, we increment row_count I and col_count j. This pre-computes the number of black pixels in all rows and columns, enabling O1 lookups for validation later. After counting, we focus on identifying candidate rows that could potentially contribute to lonely pixels. For this, we create a dictionary called row_patterns to group rows by their string representations, but only if the row contains exactly in black pixels. Each pattern acts as a key, and the value is a list of row indices that share this pattern. This grouping simplifies the task of validating the identical row condition, as we can now refer to rows by their patterns instead of repeatedly comparing their content. With the candidate rows identified, we now count the lonely black pixels. We initialize lonely_count to 0 and iterate through the grid again. For each black pixel at I, j, we check two conditions: whether the row and column counts match n, and whether the row pattern for the pixel matches the pattern of all rows contributing to its column count. If both conditions are satisfied, the pixel is considered lonely, and we increment lonely_count. After examining all the pixels, the final value of lonely_count is returned as the result. By combining pre-computed counts with row pattern validation, this step ensures that we efficiently and accurately determine the number of lonely black pixels in the grid. Several key insights make this algorithm efficient and effective. First, pre-computing the counts of black pixels in rows and columns eliminates redundant computations during validation. Second, using string representations to group rows simplifies the process of verifying identical row configurations. Third, the algorithm is naturally optimized for sparse grids, as it focuses only on black pixels, ignoring white ones. It's also robust enough to handle edge cases, such as grids with no black pixels, small grid sizes like 1x1 or 2x2, and scenarios where no rows or columns meet the end condition. The data structures we use, specifically the 2D grid, count arrays, and row pattern dictionary, work together to efficiently solve the problem while maintaining clarity and simplicity. The algorithm's time complexity is O(m*n), where we first count the rows and columns and then validate the lonely black pixels, both requiring a full traversal of the grid. The space complexity is O(m+n), as we use auxiliary arrays for row and column counts, along with additional space for the row patterns dictionary. This approach ensures a scalable solution even for large grids. The algorithm handles various edge cases, such as an all-white grid where the result is 0, a single black pixel in a 1x1 grid with n equals 1, and grids with multiple rows sharing identical patterns. It also accommodates rectangular grids of different dimensions, demonstrating its flexibility and robustness in solving the problem efficiently. Here, we define a class called solution and implement the method findBlackPixel, which takes in a 2D list called picture and an integer n. The picture represents the grid of pixels, where B stands for black pixels and W stands for white pixels. The goal is to find the number of lonely black pixels that satisfy the given conditions. First, we determine the dimensions of the picture, storing the number of rows in M and the number of columns in N. Next, we calculate the number of black pixels in each row using a list comprehension, storing these counts in the row_counts list. Additionally, we initialize a call_counts list to track the number of black pixels in each column. Using nested loops, we iterate through each column and row, incrementing the corresponding column count whenever we encounter a black pixel. Afterward, we group rows by their string representation to identify rows with exactly n black pixels. This is achieved by iterating through each row and converting it to a string using the join function. If the row contains exactly n black pixels, we check if this row string already exists in our row_groups dictionary. If not, we initialize an empty list for it. Then, we append the row index to the corresponding list in the dictionary. At this point, we prepare to count the lonely black pixels by initializing a variable called lonely_black_pixels to 0. Finally, we start examining each group of rows in the dictionary to determine if they meet the conditions for contributing to the count of lonely black pixels. If a row group contains exactly n rows, we proceed to check each column in the row string representation. For every column where the character is B, meaning it represents a black pixel, we verify if the total count of black pixels in that column is also equal to n. This ensures that the column satisfies the condition for a lonely black pixel. When both conditions are met, we add n to the lonely_black_pixels count, as each column contributes n lonely pixels for the rows in the group. After iterating through all the row groups and columns, the method concludes by returning the total count of lonely black pixels. This approach efficiently combines row and column constraints to solve the problem while ensuring the conditions for n are met. Here, we start by defining the method findBlackPixel, which takes a 2D character array picture and an integer n as inputs. The first step is to determine the dimensions of the picture matrix, storing the number of rows in M and the number of columns in N. Next, we initialize two arrays, rowCounts to track the number of black pixels in each row, and callCounts to count black pixels in each column. These arrays are essential for identifying rows and columns that meet the criteria later on. We then loop through the matrix using nested for loops. For each cell in the matrix, if the character is a B, we increment the corresponding row and column counts. This gives us a clear picture of how many black pixels are present in each row and column. After this, we group rows by their string representation. To do this, we iterate over all rows, and for rows where the count of black pixels matches n, we convert the row to a string and store it as a key in the rowgroups map. The value for each key is a list that keeps track of the row indices for rows with identical patterns. Now, after grouping rows by their string representation, we initialize a variable lonely black pixels to 0. This variable will store the final count of lonely black pixels. We then iterate through each entry in the rowgroups map. For every entry, we extract the row string and the list of row indices. If the number of rows in the group equals n, we proceed to check the columns. For each column index, we look at the corresponding character in the row string. If the character is a B and the count of black pixels in that column also equals n, we know this column satisfies the criteria for lonely black pixels. Since all rows in the group are identical, we can directly add n to our counter for each valid column. Finally, after finishing all these checks, we return the total count of lonely black pixels. This ensures that the algorithm correctly identifies and counts all the black pixels that meet the given conditions. To solve this problem, we first need to analyze the input picture and initialize some variables. The picture is a 3x5 grid where W represents white pixels and B represents black pixels. The task is to find lonely black pixels where the number of rows containing identical patterns of black pixels equals the number n, which is given as 2 in this example. We start by determining the dimensions of the grid. There are 3 rows and 5 columns. Next, we initialize two arrays, row_counts to count the black pixels in each row, which is initially 2, 2, 2, since each row contains exactly 2b pixels, and call_counts, which keeps track of black pixel counts in each column and starts as 0, 0, 0, 0, 0. Now, we proceed to count the black pixels in the columns. By iterating through the rows, we find that column 1 has 3 black pixels, so col_counts becomes 0, 3, 0, 0, 0. Similarly, column 3 also has 3 black pixels, updating col_counts to 0, 3, 0, 3, 0. This completes the first step of the process. After counting the black pixels, we group rows by their string representation. In this example, all rows share the same pattern WBWBW, so we create a dictionary row_groups where the key is the string WBWBW and the value is a list of indices, 0, 1, 2, representing the rows that match this pattern. Now, we need to check these row groups to identify lonely black pixels. For the group WBWBW, there are 3 rows that match the pattern, which is equal to n. This makes the group a valid candidate. We then check the columns where black pixels appear in this pattern, columns 1 and 3. For column 1, the total black pixel count from col_counts is 3, which matches the row count, so we add 3 lonely pixels. Similarly, column 3 also has a black pixel count of 3, adding another 3 lonely pixels. In total, we find 6 lonely black pixels, and the output for this example is 6. Now, let's consider a second example to illustrate a case where there are no lonely black pixels. In this new example, the input picture is a 3x3 grid, and n is 1. After analyzing the grid, we initialize the dimensions as 3 rows and 3 columns. We calculate the black pixel counts for the rows and columns. Row_counts becomes 1, 2, 1, since the first and third rows each have 1 black pixel, and the second row has 2. Similarly, col_counts is 1, 2, 1, reflecting the black pixel counts in each column. Next, we group rows based on their string representation. The first and third rows share the pattern WBW, so row_groups is WBW, 0, 2. The group WBW contains 2 rows, but since n is 1, the group is not valid because the row count does not match n. As a result, we skip this group. Since no other groups meet the criteria, there are no lonely black pixels in this example, and the output is 0. Now, let's look at a final example where there are multiple valid row groups. In this final example, the input picture remains a 3x3 grid, but n is now 2. We start by initializing the dimensions, 3 rows and 3 columns. The black pixel counts for rows are 2, 2, 1, and for columns, they are 2, 1, 2. Next, we group the rows by their string representation. The first 2 rows share the pattern BWB, so row_groups becomes BWB, 0, 1. The group BWB has 2 rows, which matches n, making it a valid candidate. We then examine the columns where black pixels appear in this pattern, columns 0 and 2. For column 0, the total black pixel count is 2, which matches the row count, so we add 2 lonely pixels. Similarly, column 2 also has a black pixel count of 2, adding another 2 lonely pixels. This gives us a total of 4 lonely black pixels, and the output for this example is 4. To analyze the time complexity of our solution, we start by breaking it down into distinct operations. First, we calculate the black pixel count for each row. Since there are m rows in the picture and each row contains n columns, counting the black pixels in a single row takes n. Repeating this for all rows results in a total time complexity of m*n for this step. Next, we determine the black pixel count for each column. There are n columns, and for each column, we iterate through all m rows to count the black pixels. This also results in a total time complexity of m*n. Finally, we group rows based on their string representation. Creating the string for a single row takes n, and we check if the row has exactly n black pixels. If it does, we store it in a dictionary. Operations involving the dictionary, such as insertion or lookup, are 1 per operation. Since we process m rows, this step also contributes m*n to the overall time complexity. Now, we analyze the step where we check the row groups. For each unique row string in our dictionary, we verify if the group contains exactly n rows. Let's assume there are g unique row strings. Checking the size of each group is an O1 operation. For each group, we then iterate over all n columns to check if each column contains exactly n black pixels. This process takes n for each group. Therefore, the total time for this step is O, G asterisk n. Importantly, the number of unique row strings, G, is bounded by the total number of rows, M. Summing up the contributions from all steps, the overall time complexity of the algorithm is O, M asterisk n. Even though the term O, G asterisk n arises here, it is dominated by the earlier processing steps, making O, M asterisk n the final complexity. Moving on to space complexity, we begin by looking at the memory used for storing black pixel counts. We maintain two arrays, one for row counts and one for column counts. The row counts array has a size of O, M, while the column counts array has a size of O, N. Together, these contribute O, M plus N, space complexity. Next, we consider the dictionary used to group rows by their string representations. In the worst-case scenario, all rows are unique, meaning we would store M keys, each being a string of length n, along with their respective indices. This results in O, M asterisk n, space for the keys and O, M, for the values. Thus, the dictionary contributes O, M asterisk n, in total. Finally, the algorithm uses constant auxiliary space for variables, which adds O, 1. Summing these, the overall space complexity is dominated by O, M asterisk n. Adding up all the contributions, the total space complexity of the solution is O, M asterisk n, in the worst case. To provide context, let's compare this optimized approach to the naive method. A brute force solution would involve iterating over all rows and columns to validate every possible lonely black pixel. This would require O, M asterisk n, for the outer loop and an additional O, M asterisk n, to check row and column conditions for each pixel. The resulting time complexity would be O, M squared asterisk n squared, which is prohibitively expensive for large inputs. By contrast, our optimized approach leverages pre-computed counts and a dictionary to group rows efficiently. This reduces redundant checks and achieves an overall time complexity of O, M asterisk n. The space complexity, although still O, M asterisk n, is a reasonable trade-off for the significant improvement in runtime. Let's now consider the best, average, and worst-case scenarios for this algorithm. In the best case, where n is 0, the algorithm avoids most of the processing because no rows or columns meet the criteria. In this situation, the time complexity simplifies to O, M asterisk n. For both average and worst cases, the algorithm processes each row and column, ensuring all conditions are checked. This results in a time complexity of O, M asterisk n, for general inputs. The space complexity remains O, M asterisk n, across all cases due to the dictionary storage. In summary, the optimized solution improves significantly over the naive approach by reducing redundant operations through pre-computation and efficient data structures. With an overall time complexity of O, M asterisk n, it is well suited for handling large input sizes efficiently. Now, let's talk about some common mistakes that can occur while solving this problem. First, one of the most frequent errors is not accounting for edge cases during grid traversal. For instance, you might encounter grids with no black pixels at all, or grids that consist of just a single row or column. If these cases aren't handled properly, they can lead to index out-of-bound errors or produce incorrect results. Another issue arises from inefficient repeated computations. In a brute force approach, scanning rows and columns multiple times for each black pixel significantly increases the time complexity. A better strategy is to pre-process the grid to count the number of black pixels in each row and column first, which avoids redundancy. Additionally, it's crucial to correctly interpret the condition for a black pixel to be considered lonely. Remember, the pixel must be the only black pixel in both its row and column to qualify. Overlooking either of these conditions leads to errors. Off-by-one indexing errors are another common pitfall, especially with zero-based grids. For example, you could inadvertently skip the first or last row or column if your loop boundaries aren't carefully set. Finally, for large grids, performance constraints are critical. A brute force solution with O, N squared, complexity becomes impractical for grids as large as 10,000 by 10,000. Always aim for a scalable and optimized approach. To perform well in interviews, there are several key strategies to keep in mind. Pre-processing the grid for efficiency is one of them. Instead of scanning rows and columns repeatedly for each black pixel, pre-process the grid to count the number of black pixels in each row and column. This approach minimizes redundant checks and significantly improves performance. It's also essential to clearly communicate edge cases during the interview. For example, mention how you would handle empty grids, single rows or columns, or grids without any black pixels. This demonstrates your thoroughness and attention to detail. Additionally, be prepared to discuss space-time trade-offs. Optimized solutions often require extra space, such as arrays to store row and column counts, in exchange for faster computations. Make sure you can explain why this trade-off is beneficial in the context of this problem. Lastly, always test your solution thoroughly. Start with small grids, like 3x3 or 4x4, that have varied distributions of black pixels. This helps ensure your logic is sound before scaling up to larger grids. This problem shares similarities with several related problems that can help you deepen your understanding of grid-based algorithms. For example, LeetCode 73, Set Matrix Zeros, involves modifying a grid based on specific constraints, while LeetCode 36, Valid Sudoku, focuses on validating a grid structure. LeetCode 766, Toeplitz Matrix, and LeetCode 200, Number of Islands, also deal with traversing and analyzing grid patterns. Exploring these problems can give you additional insights and techniques applicable to Lonely Pixel 2. When it comes to alternative approaches, the brute force method is the simplest to implement. However, it has an n-cubed complexity for large grids, as each black pixel check requires scanning its entire row and column. While this approach minimizes space usage, its performance is impractical for larger inputs. A more efficient solution involves pre-processing the grid. By using arrays to store the count of black pixels in each row and column, you can reduce the complexity to n squared. This method is faster but requires additional space for the count arrays. Another option is the hashmap approach, which stores row and column counts in hashmaps instead of arrays. This is particularly useful for irregular grids or dynamic cases. However, it's slightly slower than the array-based method due to the overhead of hashmaps. Each approach has its trade-offs, so choose the one that best fits the problem constraints. Thank you for joining this session. Today, we explored the Lonely Pixel 2 problem, discussed a brute force solution, and identified key optimization areas. Remember, understanding the trade-offs of each approach is a vital skill in programming. Don't forget to practice and stay curious. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!